Okay, hello everyone. Here I'm Alexey, and here we continue our tutorials on Libra, and this time we'll be talking about analyzing time series of some data and computing the autocorrelation function of this data, and also extracting some additional information from the ACF or from this data eventually. Now here I'm in this test 13 ACF folder of the test Libra PY directory, and it contains only this test.py file, which is pretty much straightforward. We load all the variables, all these modules, and here we define this run test function, which basically does the following. So here we define our data, and we populate our data with a bunch of vectors, which are like three-dimensional vectors, and each component of the vector is basically a trigonometric function of time, sine or cosine, with different omegas frequencies. And here we define these frequencies in the wave numbers, so this is basically what we want to define, and then later we basically and also it's important to generate time in the proper units. So that's why we also do all the conversion from the to some femtosecond. So we assume this time is in femtosecond, and then we do all the conversion. And once the data are generated, we call the function called recipe1 from the ACF module of the Libra PY module, to do the processing. So it takes the data and some parameters. So why are data represented as a list of vectors? Because like for typical chemical applications, you, for instance, might want to compute the IR, infrared spectra, and they are computed by using electric dipole moment. So you can run an equilibrium molecular dynamics simulation, and then from that simulation you will sample a time series of the electric dipole moment of your molecule, and then you can compute ACF of the electric dipole moment, and by doing the Fourier transform you can extract the frequencies, all the frequencies that are, or the modes that are active in the IR spectrum. So so that's what this recipe one is basically doing. So like essentially the computational part is here. Everything else here is just to mimic collection of the data. Okay, now let's look at what the ACF function is doing, and specifically what is this recipe one is about. So recipe one takes these parameters, data, doesn't matter which units, what sort of data it is. Could be velocities, could be forces, positions of your atoms, or this could be electric dipole moment of your system, and so on. And for instance, if you really want to look at some scalar data, right, then you can just use the same list of vector objects, but then set only one component of these vectors, let's say x, to the scalar property you want, and set everything else to 0. So this is pretty general function in that sense. And then the frequency span and the frequency step supposed to be in the wave numbers, so it's convenient. Here we do all the conversion to internal units, and then we do this centering of the data so that the average for all the mean of each component is 0, and then so that will be a new list of vectors, and then that list of vectors will be transformed by ACF. Why do we center it? Because we by doing this we actually remove the zero frequency modes, and the zero frequency modes are basically translation. So that means your system will be flying in a space, for instance, and you don't really need that information about the zero. That will basically be speed of your of the center of mass. Now so once it's done, the function generates the raw. Well, this is supposed to be RAW ACF and normalized ACF, and this will be our time series and specified units. Then we print out everything in the file, and then after that we also run another function ft, which is a Fourier transform of the normalized ACF. And then the output will be determined by the range of the frequencies and the distance between the frequency points, and also input timescales. So as a result, you will get these frequencies that will define your x-axis of IR, for instance, plot, and J will be the intensity or like power spectrum of your data. So and then this information is also written into the file, which ends the execution of this recipe 1. So now let's look at how this all works, and to do that we'll go to higher here. We'll go to test Libra PY, then we go to test 13 ACF, and this is actually a part of the Libra distribution. So now we can just run python test.py. This all output is doesn't matter. What matters is that we now generate this ACF function, which contains the time in the femtoseconds, right? And also the second column will be normalized, and then unnormalized ACFs. And then also we generated the spectrum file, which now also contains the frequencies in the wave numbers in the range that we defined. So we defined this sort of range, and then the second column contains the J, which is intensities of this frequencies. So now we can basically plot everything. And here's my plotting script. So ACF, we will load the ACF function, and then here we can also plot the the spectrum. So we do GNU plot now, and that generates these two files. One is ACF, so that's how it looks like. You see different frequencies here. Some of the longer, larger time frequencies, other more higher frequency modes. So and essentially this is how you define the data, right? And this is your the spectrum, which shows the modes that you defined. So let's look at that again. So we had 150, 100, on just 500. Okay, do we have 5? All right. So 500 no. This is no. Okay, so these are frequencies somehow shifted. That is kind of strange. But yeah, but basically, so I need to look more carefully at this moment. So I will see what happens, but eventually you do see these three frequencies that you initially defined. So let's maybe play with this script. Let's see what happens if you define 1000, 1000, and 1000. Right, so just three frequencies the same, so will be some simplified spectrum, but then I will maybe get some idea on how to correct it. So let's run the plotting. This is my ACF. Now you can see this sort of regular um, regular oscillations with only one frequency, and oh, okay. So I think I know what is the problem. The problem is that here in uh, we probably need to set y range to a bigger number. So let's put it to this number and then plot again. Oh, what about what about if we use something bigger like that? Oh. Oh, okay. Now here we go. So now it makes more sense, and you really see this sort of peak with a single frequency. So let's maybe make it even bigger, 2000. So and yeah, so this is actually your single frequency 1000 as you have defined, and all these other lines, this basically gives you the resolution. So the resolution of your spectrum will be higher the more points you have. So let's, for instance, sample not 1000 points, but let's do 10,000 points and a single frequency. So that takes a little bit longer time to compute, and eventually here we can plot what we've got. This ACF doesn't change. Now here we get like much better resolution in like this huge peak. So which is kind of continuous and broadened. So yeah, so essentially everything works pretty well. Now let's go back to this original example. So with a smaller number of steps, just 1000, and so we had only 500, 500, like 14 and 850, right? That was our original setup. So let's run this calculation again, and basically that was the problem of plotting. So now we should see, yeah, and that's exactly what you see. This is 500 peak. Here's another peak at 850, and this is like 1400 peak. So this is basically really working example, kind of showing the meaning of this and the utility of this ACF function in its transform. So you can, and essentially if you have some data which you don't know how to analyze, let's compute it ACF, normalized ACF, Fourier transform, and then you will see the modes like the frequencies that are characteristic to that time series, and in chemical applications that will mean IR frequencies or some other electronic transition frequencies. So on that, let's finish this tutorial and have a good day.